Hi, my name is Josh Marchant, and today I'll be presenting on the effect of bone model geometries on the determination of skull acoustic properties using ultrasound simulations and optimization. The successful delivery of high-energy doses at a focal point in transcranial magnetic resonance-guided high-intensity focused ultrasound treatments depends largely on ultrasound beam focusing during the treatment. Improved focusing can be achieved by phase aberration correction methods if the acoustic properties of the skull bone are known. However, current literature shows significant disagreement regarding the values for acoustic attenuation in human skull bone, and some disagreement regarding skull speed of sound. Therefore, our goal was to determine the effect of skull bone internal geometries on the resulting values found via optimization. We first created several 3D numerical bone models with varying internal geometries. Through transmission was simulated using the hybrid angular spectrum method, or HAS, in MATLAB. Next, we sought to characterize the cost function behavior for each acoustic parameter over a small window of values defined as the solution space. Finally, we tested each model using an optimization algorithm to see how well each parameter could be determined. The following 3D numerical models were created. Each quarter millimeter isotropic model had two bone types defined numerically as either cortical bone or diploid. Set A models, shown here as cross-sectional cuts of the total volume, had basic geometries designed to investigate the effect of various layer patterns in the model on the final output pressure pattern. Set B was composed of 33 models, only 3 of which are shown, whose diploid thickness varied sinusoidally in the x dimension. Models in Set B were labeled according to their spatial period in number of voxels. Therefore, B10 had a spatial frequency of about 0.4 inverse millimeters. Set C included 3 thicker models, whose internal geometry varied sinusoidally in both the x and y dimensions across the bone, and included a low, high, and combined spatial frequency model. Set D included 3 models generated using high-resolution micro-CT scans of segments of excised human skulls. These models were segmented into cortical and diploid bone according to selected Hounsfield unit thresholds. Each bone model was assigned the following acoustic properties as true values, which the optimization algorithm would attempt to determine. These values were derived using a Hounsfield unit to acoustic property relationship as referenced below. To perform the ultrasound simulations, the hybrid angular spectrum, or HAS method, was employed. HAS allows for the rapid simulation of ultrasound transmission through inhomogeneous media by alternating between the spatial and frequency domains. This process is described in detail in the reference publication. Because HAS is more computationally efficient than most wave modeling strategies, it presents a promising alternative when performing iterative and computationally heavy optimization tasks. The experimental setup for each simulation was structured as followed. We simulated an unfocused planar transducer with a large emitting diameter of 19 millimeters, placed to the left of the beam. The bone model was placed at approximately 200 millimeters in the z direction from the transducer face. This constituted the far field range for the simulated beam at all frequencies. To characterize the field, we define the transmitted amplitude ratio as the ratio between the magnitude of the pressure field at the measurement plane with and without the bone model in place. We use the RMSE, or the sum of the squared differences of all voxels between the test and the truth transmitted amplitude ratios, as the cost function for each trial. We first aimed to characterize the solution space for each model before performing optimization. The solution space was defined as the image representation of the cost function versus the cortical bone and diploid acoustic properties. As shown, these changes were iteratively adjusted over a small range centered about the true property values for each bone type. Several selected examples of the solution space searches are shown. In the leftmost column, the fractional diploid thickness, defined as the number of diploid voxels versus total voxels, depicts the internal geometry of each model. The middle and rightmost columns show the solution spaces with overlaid contour lines to enable improved visualization. The most ambiguous solution spaces were produced by models with only high spatial frequency internal geometries. The solution spaces were designed to serve as clues to indicate how well the optimization might perform. Next, we employed the surrogate optimization algorithm available in MATLAB's global optimization toolbox, termed SurrogateOpt. This was well suited to our task because it decreases computational time and is capable of handling unknown cost function behaviors. Each model was tested 5 distinct times to account for any bias in initial value selection. The following ultrasound frequencies were tested. Set B was tested with all frequencies to investigate the effect on the output pressure field with respect to the spatial frequency of the internal geometry of each model. The following shows the progression of the surrogate optimization towards the minimum. For set B, an approximate spatial frequency cutoff for each frequency was found, indicated by the dotted line. Increased spatial frequencies resulted in an increased error, as seen to the left of the plot. The transmitted amplitude ratio shows that the internal geometries were not properly resolved for spatial frequencies above this cutoff. When grouped above and below this cutoff, all models above the cutoff in set B showed an increase in error. Model C2, the set C model, with only a high spatial frequency component, also showed increased error. The attenuation values for set D were determined with low error and variability. The speed of sound values were also determined with low error and variability for all models tested. Using various three-dimensional models, we determine the impact of internal geometries on property determination using surrogate optimization. The attenuation coefficient was found with increased accuracy when the internal geometries were fully resolved. In contrast, models with high spatial frequency above the limit resulted in greater error. The speed of sound was determined with low error for all models. The internal structure of the three CT-based models was sufficiently resolved to allow for the successful determination of their attenuation and speed of sound. Future work to expand upon these findings may include the investigation of other physical phenomena such as scattering models or a Hounsfield unit-dependent range of acoustic parameters, experiments to identify the effect of other errors such as registration, noise, and scanning resolution, and the validation of the reported results using physical experiments. I would like to thank our stellar team at UCARE for the support of this work, as well as our funding sources. Thank you for your attention.